Okay, welcome to Lecture 2 for Unit 8. Today we're talking about the atmosphere and measuring atmospheric pressure in the atmosphere. So the image you can see right here is an image of kind of like a little slice of the atmosphere sort of shown here. This is going to kind of set us up for today. All right, so what are we looking at here? Well, we're looking at, this is obviously ground level, right, where people live, all right, and we're looking here. As you go up, what do you notice? All right, well, you notice these little blue dots start to become less frequent, right? So you can see more of them here and less up here. Well, what's going on there? It's telling you that the amount of, is it the amount of air? Is there just more air here, right, and less air here? Kinda. But today we're talking about pressure, so we're going to understand why there's greater pressure lower and less pressure up here in the upper layers of the atmosphere. Okay, we're also going to talk about how you measure atmospheric pressure and pressure in general, the units you use, and some of the tools scientists use, and meteorologists and climate scientists use to measure atmosphere. So let's get started. So atmospheric pressure, by definition, is the force per unit area that's exerted on a surface by the weight of the atmosphere. All right, so believe it or not, like, you here on the surface, you actually are getting pushed down on by the air above you, right? So all this air, if you're, here at sea level, all the air above you actually has a weight and it pushes down on you. We're kind of used to it. We've sort of become adapted to living in this pressure, so we don't feel it, but that pressure is all around us all the time. So the force of gravity holds the gases in the atmosphere near the Earth's surface. So as a result, the air molecules are compressed together, right? So these particles get kind of squished together because of gravity, kind of like the picture you saw before, and exert force on the Earth's surface. The atmospheric pressure is exerted equally in all directions, so up, down, and sideways. So we don't feel atmospheric pressure. You don't get atmospheric pressure exerted just on your head or your shoulders, the top parts of your body. It's distributed all over your body equally. All right, and that's kind of what makes it feel like not so great, right? Because it's spread throughout your whole body equally, so that pressure's kind of, spread out everywhere. So Earth's gravity, again, keeps 99%, almost all of the mass of the atmosphere within 32 kilometers of the Earth's surface. So because gravity is kind of pulling that atmosphere in, it doesn't leave. It doesn't dissipate and head off into outer space. It stays close, okay? The pull of gravity is not as strong at higher altitudes, mainly because there's a law, one of Newton's laws. It's a universal law of gravitation. The farther away an object gets from another object, the weaker that force of gravity gets, right? So if I have an object here and another object here, the farther they get from each other, the weaker the force of gravity is. So what does that mean? That means that as you go, if we're here on Earth, and here's the atmosphere, the higher you go in the atmosphere, you get farther from the Earth, so the force of gravity is a little bit weaker. So air molecules are farther apart and exert less pressure in each other at higher altitudes. Thus, atmospheric pressure decreases as altitude increases. So pressure, we'll label it PA as, let me just delete that real quick. Okay. As pressure, sorry, once again, let me make this a little bit brighter so you can see. All right, that'll work. That's better. As altitude increases, pressure decreases. So there's the A going up and the pressure going down, okay? This is one of the reasons, if you ever see someone climbing a mountain or going up really, really high, they wear like a mask, right, to give themselves some extra oxygen. You see the football players playing in Denver can hardly breathe, mainly because there's less oxygen out there. Those particles are farther apart the higher you go. So in general, as temperature increases, atmospheric pressure at sea level decreases. So warmer places have a little bit lower atmospheric pressure. Similarly, air that contains a lot of water vapor is actually less dense than drier air, because water vapor molecules have less mass than nitrogen or oxygen molecules do. This might be kind of counterintuitive. You might think, like, if there's a lot of really humid air, a lot of water vapor in the air, that is going to be more dense, right? Because there's more stuff in there. But it's actually less dense because, as we just stated, water molecules are they carry less mass. Remember the formula for density, right? So density equals mass over volume. And if you decrease that mass, well, then the overall density, is going to change. It's going to get lower. So how do we measure atmospheric pressure? Meteorologists use 3 units for measuring atmospheric pressure. All right, so the first is called just an atmosphere. It's actually the unit, the atmosphere, and it's abbreviated with ATM. Millimeters of or inches of mercury, depending on where you are. So it's how much. We'll explain a little bit more about that in a second, but that's the unit. It's millimeters of mercury, and millibars. All right, so standard atmospheric pressure, or 1 atmosphere, is equal to 760 millimeters of mercury, or 1,000 millibars. So if you kind of like set these all equal, you'd write 1 ATM is equal to 760 millimeters of mercury, which is equal to 1,000 millibars, or M. Oops. I got my unit for mercury wrong. Oh, okay, sorry about that. Mercury is, of course, Hg. All right, so that's kind of, so if 1 atmosphere is equal to 760 millimeters, and so on. Okay, meteorologists use something called a barometer to measure atmospheric pressure. All right, so barometers are kind of like, they do the same thing a thermometer does, but they just tell you about atmospheric pressure. All right, so if you are a real weather nerd, you actually really want to pay attention to your barometer just as much as you would your thermometer, because you can learn a lot from the change in atmospheric pressure. More on that another day. There's a few different kinds of barometers. One is called a mercurial barometer. So you hear the word mercury in there. Now we're understanding why it's called millimeters of mercury. So atmospheric pressure presses on liquid mercury in the well at the base of the barometer, right? So think about it. It looks kind of like a thermometer. There's a little bit of mercury down there, and that pressure pushes down on the mercury, right? Just like it does push down on us. So the height of the mercury inside the tube varies depending on the atmospheric pressure, right? So if there's more pressure, that mercury, I'm going to change colors here. Let's make it blue. If there's more pressure, that mercury is going to get pushed up higher and higher inside this tube, right? And if there's less mercury, that the level will go down. The greater the atmospheric pressure is, the higher that mercury rises. So it sort of, again, does what a thermometer does, as that level goes up. It tells us an increase or decrease in atmospheric pressure. Here is sort of your little example here. So on the left here, you can see a glass tube. So greater air pressure forces that mercury up a little bit higher. I've got one of these I can show you in class what it looks like here, if you'd like to see it. And over here on the right side, if you use water instead of mercury, the question says, why is the water column much higher than the mercury column? Because mercury weighs more than water. So we use mercury mainly because we can make a smaller little object. We don't have to make this giant thing here on the right. Mercury is much more dense than water, so it makes an ideal little tool to make a small barometer. All right, finally, the next kind of barometer, there's one kind of barometer called an aneroid barometer. So inside an aneroid barometer is a sealed metal container. Sometimes they're actually kind of coiled like that, for which the air has been removed to make a partial vacuum, so no air. Changes in the atmospheric pressure on the outside, right? So again, the atmospheric pressure is going to sort of push down on that tube, right? It's going to push down in all directions. So changes on the outside cause the containers to bend inward or bulge out. So it's going to cause that coil or that spring or that area to change its shape. These changes move a pointer on the scale. So there's the pointer right there. The aneroid barometer can also measure altitude above sea level. We've got one of these in the classroom. Just ask me to grab it and I'll show you. It's a really cool old one. It actually draws the air pressure on a little piece of paper, kind of records it almost like a seismogram. You can see that. Okay, so that's all we got so far. So thinking back, we've learned that we measure atmospheric pressure in atmospheres, millimeters of mercury, and millibars. Those are the 3 units. As you go up, And in altitude, atmospheric pressure gets lower, right? It's because gravity is a little weaker, so the particles are less compressed together, right? They're kind of flowing more freely, so there's less pressure up there. So if you climb up to the top of a mountain, there is a lower pressure up at the top than there is down here, right? So it's a little higher pressure down below, okay? Because there's more air pushing down on you. That's pretty much it. Pretty short little lecture here. You'll have a few questions. You can use your notes in this quiz, I think. So come in, be prepared, and get ready for your quiz. Have a good night, guys. If you have a question, shoot me an email. If you didn't understand something or missing some notes, let me know. Take care.